In this video, we're going to talk about percent yield, which is target 7.7. When we do this video, we're going to need a periodic table and a calculator out. We're going to use some concepts we've learned in stoichiometry in order to calculate percent yield. So make sure you are calculating with me and following along using your periodic table. Couple things we need to know before we can calculate percent yield. There's two key terms. The first is the actual yield. What does actual yield mean? Well, it's the amount of product, and that's really important that it's a product, not a reactant we're talking about, that is produced in an experiment. So if it's produced, that means it has to be a product. Remember, your experiments make a product. So your balance equation gives you a product. So it's going to be on the right side of your equation. The actual yield, this is going to be given to you in the problem. So it will be given to you. Or if you're doing lab, it comes from your lab data. So look at your data table when you're doing a lab to find your actual yield. Your theoretical yield, on the other hand, this is the amount of product. Again, it's a product. It'll be the same. These two will both be the same product that should be produced when you do the experiment. So when it says it should be produced, this is the maximum amount possible. So how much could you make if you made no errors? And notice it says it's going to be calculated. So you're going to use stoichiometry to calculate this number. When you do actual yield and theoretical yield, you want those two numbers to be as close to possible as possible because that means you had no percent error. So again, the actual yield is going to be given or it's from your data, and then the theoretical yield, it's going to be a calculation. Put those two things together and you get the percent yield. So here's your equation for percent yield. It's the actual yield over the theoretical yield times 100%. Since it's a percent, your units are going to be percentages. That's why we multiply by 100. And the other thing I want you to note is that the percent yield is only for a product. You never calculate the percent yield for a reactant. So make sure that when you're calculating the percent yield, you're using a product, something that's on the right side of your balanced equation, what the arrow in the balanced equation points to. So actual over theoretical times 100. And this number, this percent, should never be over 100% because you can't create or destroy matter, which is what the law of conservation of mass says. So over 100% would mean you created something, and that's impossible. So make sure that this number is less than 100%. Otherwise, you made some sort of a mistake. So check your work. So let's do an example. The first one is talking about limestone, which is calcium carbonate, and it says calcium carbonate decomposes. Remember, decomposition reaction is when you start with one reactant and break it into two or more products. So calcium carbonate, it's decomposed into carbon dioxide and calcium oxide when it's heated. Then it says you have 17.5 grams of carbon dioxide. It's produced from the decomposition of 42.73 grams of calcium carbonate. What is the percent yield of the reaction? Hint, start with a balanced equation. So anytime that you have a percent yield problem, you're going to have a balanced equation. So if one is not given to you, make sure you write one and make sure it's balanced and your formulas are written correctly. So let's go back to the beginning. Calcium carbonate decomposes. So got to look at our periodic table. Calcium is a metal and it has a charge of +2 and it's an ion. Carbonate is one of your polyatomic ions and it's CO3 -2. So our charges cancel out. So we have CaCO3. And it's decomposition, so that's our only reactant. It decomposes when heated, so I'll put the triangle over my equation because it's heated. And it produces, or it turns into carbon dioxide. So notice it's a di here. That means it's a covalent compound. You have carbon and oxygen, both nonmetals, so you don't have to worry about balancing charges. They'd both be anions, so they'd both be negatives, and they wouldn't be able to cancel out. So carbon dioxide, di is 2, so CO2. Plus, we also have calcium carbonate. So if we look at calcium carbonate, calcium's +2. I'm sorry, not calcium carbonate, calcium oxide right there. So calcium's +2, oxide is -2 if I look at oxygen from the periodic table, and that makes CaO. Now, the last thing I want to do before we move on is make sure our equation is balanced. And it looks like it is. I have one calcium on both sides, one carbon on both sides, and in the reactants, I have three oxygens, but on the products, I have two from the carbon dioxide plus one from the calcium oxide, so that adds up to three. So we're all balanced. If it helps, you can write your coefficients of 1 here, but you don't need to. All right, I'm going to go back and read the problem and just kind of pull out the information. It tells me I have 17.5 grams of carbon dioxide. So I'm going to write that here, 17.5 grams of CO2 and 42.73 grams of calcium carbonate. Sometimes it helps to write the information in the problem under the balance equation, then you don't have to keep looking at the equation. So let's look at the information and think about this. We're asked to find the percent yield. We know that percent yield is going to be the actual yield over the theoretical yield times 100. And we said the actual yield is always given to you, and it has to be for a product. So is calcium carbonate or carbon dioxide the product? Because that will determine it, which one of these numbers is our actual yield. Well, carbon dioxide is the product, so this is our actual yield. So we already know the numerator of our equation. We just have to find the theoretical yield. So in theory, how much carbon dioxide could we make if we used all 42.73 grams of calcium carbonate? So let's start with that. We'll do some stoichiometry. 42.73 grams of CaCO3. And we're going to turn that into grams of CO2, and this will give us our theoretical yield. So we know to get rid of grams, we have to use molar mass. Use your periodic table, calculate the mass of a calcium, a carbon, and 3 oxygens. So we have 1 mole of CaCO3. I calculated that out to be 100.09 grams of CaCO3. So that gets rid of the grams. I have moles now of calcium carbonate, but I'm looking for carbon dioxide. So look at your balanced equation. Carbon dioxide and calcium carbonate are both in there. There's a 1-to-1 ratio. So we have 1 mole of CO2 to 1 mole CaCO3. Now I have moles of carbon dioxide. I'm going to find the molar mass of carbon dioxide. Again, you probably should pause the video or try to do it on your own just to make sure you've got it. And you get 44.01 grams of CO2. So moles of CO2 cancel. Now we have grams. I plug that all into my calculator and I end up with 17.9 grams. I rounded to 4 significant figures because 42.73 had 4 significant figures. What we just calculated is our theoretical yield. So now we have our actual yield and our theoretical yield. Let's plug it in. So percent yield would be equal to 17.5 grams of CO2 to 18.79 grams of CO2. Notice I have a smaller number in the numerator than the denominator, which means I won't get over 100% and then multiply by 100. The numerator and denominator could be the same. That means you did have 0% air. So I multiply that out and I end up with 93.1%. I rounded to 3 significant figures because 17.5 only had 3 significant figures. Notice these grams of carbon dioxide cancel and my final unit is percent. So what I would do now is pause the video and try to do example 2 all by yourself. Don't just quit after example 2. Make sure that you continue to watch the video for example 3 because it's different than number 1 and number 2. And you got to make sure you can do all different types of problems. So pause, use your periodic table, your calculator, and see if you can do 2, then check back in. Okay, so hopefully you were successful. Here's my work. Notice I start with a balanced equation. It's a single replacement reaction, and I wrote down everything I have in this problem. The 6.92 grams of magnesium chloride, this would be my actual yield here. So I've got my actual yield given to me. I'm going to use the grams of hydrochloric acid and convert it to get my theoretical yield. So you can see I used molar mass, molar ratio, molar mass again, and I ended up with 7.83 grams of magnesium chloride. I plugged in my theoretical yield into my equation, and I got 93. Oop, no, you do not get that. Hang on. That's a little bit of a math mistake. That was from the last answer. You get 88.4% if you did it correctly. Okay. All right, make sure you watch number 3 because number 3 is just a little bit different, example 3, than the last 2. Okay, so we have this equation. Notice it is not balanced. I can see on the reactants I have 4 phosphorus, and on the products only 1, so I'll put a 4 in front of PF3. And now I have to balance the fluorines. On the right side, 4 times 3 is 12, so I have 12 fluorines. On the left, I'm going to put a 6 in front of F2. Okay, so now let's look at the problem. We want grams of fluorine. So if we were looking for grams of F2, and it says are needed to produce 120 grams of PF3. And it tells you the reaction is only a 78.1% yield. So it's not 100%. There's clearly some lab error in here. So let's think about this. We have percent yield formula is equal to the actual over the theoretical times 100. Well, what's this number given? This 120 grams. So that's for a product. And if it's given, we know that that's our actual yield. And we also have our percent. So we know the percent and we know the actual. We don't know the theoretical. So let's plug in and do a little algebra. 78.1 equals 120, and this is grams of PF3 to X. Now, X is going to have the same unit as the numerator, so that's going to also be grams of PF3. Might help you to write the units in there. If you're not sure what you're looking for, you don't have to, but it can be helpful. Okay, so we solve this. We start by dividing each side by 100. So we have 0.781 equals 120 over X. So cross multiply, 0.781, X is equal to 120 divided by 0.781, and you're going to end up with a value for X. So when you do all of that, you end up getting X is 154. Now, what's the unit? Well, go back to the beginning, and we said that was grams of PF3. Some students might stop here, but you're not done. It asks you how many grams of F2. So we need F2. Right now we have grams of PF3. So we're going to convert that to grams of F2. So let's do some stoichiometry and convert to grams of F2. So first we're going to use molar mass, 1 mole of PF3. Get the molar mass, that's 87.97 grams of PF3. So we got rid of grams. Moles, let's look at our balanced equation. Good thing we balanced it. We have 6 moles of F2 to 4 moles PF3. So the moles of PF3 cancel, grams of fluorine. Now we're going to use molar mass. 1 mole of F2. Now make sure you multiply the mass by 2. So 19 times 2 is 38.00 grams of F2. What's left unit-wise is grams. It looks like I started with 3 significant figures, so my answer is going to have 3, so I have 99.8. So in this problem, we started with the percent yield formula, and then we ended up doing some stoichiometry. In example 1 and 2, we started with stoichiometry, and then we got to percent yield. But notice in all of the reaction or all of the problems, we had to start with a balanced reaction or a balanced equation.